fluids equation, which is the primary equation we use for fluid flow. So this section of the chapter is called fluid dynamics. So we apply it to a variety of kinds of problems like flow of water in a tube whose maybe diameter is changing. And not only the diameter is changing, but also maybe the height is changing. So a certain fluid is entering here with a velocity v1. And then the opening of the area is a1 here. And then the fluid is constricting over here. So a certain amount of fluid is coming out here with a velocity v2, right? And then the area is a2. So if I wanted to know what v2 is, depending on what v1 and a1 are, I would need to know also their height difference, right? So I would need to know, let's say from the middle of this tube to the middle of that tube, what's that height h1, right? So what's happening here is kind of similar to what would happen to a block in physics 1. If the block is coming down the incline, right? Kind of related to this. If the block is coming down on an incline, you have here h1, and then by the time it ends up here, v1. Maybe if the initial velocity is v1, the final velocity is v2. You see it kind of similar. So here we say the potential energy initial plus the kinetic energy initial is kinetic energy final. So here we have mg h1 plus half m v1 squared half m v2 squared. Right? On top of that, if we have a force exerted on it, F1, right? That force is going to do a certain amount of work, right? So then we're going to have here, because that force is pushing it, it's going to end up with even a higher velocity, right? So then we can have here F1, the work done by that force, right? Times the distance d, right? So we have here the final kinetic energy is going to equal the sum of the initial plus the potential plus any work done, external work. Now, if there's friction here, kinetic coefficient of friction, it's going to do negative work, right? So now we have here negative mu k and d is the work that it does. So that one I need to subtract from the work that you're doing. So then I have here negative mu k and d plus. Or if I want, I can take that negative and put it here as a positive, right? So, and then just make it, say, any external force that's helping the object, I put here. Any force that's hurting the object's final velocity, I can put here. You see, so I can say, so it almost becomes a conservation of energy equation, right? Now, if I divide this by volume, look what's going to happen. I know in physics 1 we usually don't divide by volume, right? But in physics 2, since we're dealing with fluids, we divide by volume because we want to rewrite the equation in terms of density. So now this becomes density GH1 plus half density dV1 squared, half density V2 squared, and then what's the distance over volume? It almost becomes, think about volume as as the surface area. So imagine that this was a tube almost. You know, I'm trying to give a physics 1 analogy so you can see where it comes from. Volume is like almost the volume of that tube, right? So it's the surface area here times the distance d. So this one would be AD. AD. Then what happens? DD cancels, DD cancels. What's F1 over A? Pressure P1, right? And then this is friction. I'm going to express it as a pressure P2, right? P2 over A. So this is force over A. So that's going to be what? P2. I have now just derived the Bernoulli's equation, right? Pressure P1. Any pressure that's helping the final velocity goes on the left. Any pressures that's hurting the final velocity, you put on the right. So it's almost acting like friction, kind of. You see? And then you have the kinetic energy. That's it. That's the derivation of Bernoulli's equation. And it's written like this. Density GH1 plus half density V1 squared see? So that comes from simple application of kinetic energy, potential energy, any external force that's helping the block, or friction that's hurting the block. So that's kind of like that. But now we need an extra equation to give us a certain relationship between V1 and V2. Because in physics 1, we're considering the volume as staying constant, right? But here, the volume of the tube can constrict. Right? So we need an extra restriction on what happens to the velocity if the volume constricts, or if the volume opens up. What happens? Then we have, depending on what kind of fluid is it. So we're going to deal here with incompressible fluids. Incompressible fluids. So where does that word come from? So to compress a fluid means to squeeze it, right? Incompressible means that you cannot squeeze this fluid without it having some reaction to you. You can't just squeeze it. So as soon as you try to squeeze it to a smaller volume, what's going to happen? It's going to squirt out quicker. You see? Just like a water hose. Right? When you put your thumb there, what happens? Squirts out, right? So if I put my thumb here, I'm going to do it toward you guys. You see? Squirts out at a faster velocity. You see? So is water incompressible? Yeah, we could kind of model it like that. So for incompressible fluids, we say that the area A1 times V1 is equal to the area A2 times V2. So does that have the effect that we want it to have? So if the area A2 goes to 0 or gets smaller, right, what happens to the V2? Increases, right? So that is what we wanted to do. So when you put your thumb on it, and you constrict it, it is going to go faster. This quantity, AV, also has another term. It's called the volume flow rate. Because what are the units for this? This is meter squared times meter per second, right? And literally, what is that? It's meter cubed per second, which is units of what? Volume over time. So to say that the volume of fluid flowing here is equal to the volume of fluid flowing here makes that an incompressible fluid. When you try to constrict the area to conserve the amount of volume of water flowing per unit time, the fluid has to go faster. Does that make sense? Right? So this is known as definition now. AV, volume flow rate of a fluid. And sometimes it could be measured in units of meter cubed per second, or you could say milliliters per second, or centimeters cubed per second. Any of those, okay? Okay, now let's apply this to some examples. So let's say there's an airplane here. So how does the airplane get its lift from, right? So it goes on the runway, it starts going faster, 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 right? It starts going faster, and then the air starts flowing over the wings, right? So if you look at the wing, let's say the airplane builds up a speed of, I believe its takeoff speed is somewhere around 200 miles an hour. I'm just gonna guesstimate. So let's say something like 250 meters per second. Okay, so the air on the bottom of the wing is flowing 250 meters per second, let's say. But then what the air over the top of the wing is going to flow at what?
Faster.
It has to flow faster because the same group of air that meet here, they're going to meet over here together. Okay? It's like kind of like this. I think the design of the wing is like that. It goes kind of straight and then drops. So this one goes like this, then develops some turbulence. And then this one is going to have a velocity bigger. Velocity, let's say 270 meters per second. Let's guesstimate. Okay? So then what's going to happen? The faster fluid is going to have a smaller pressure, right? The faster the fluid moves. So we can apply Bernoulli's equation to this gas down here. We can say, okay, this gas is pushing up on the plane's wings. So P1 plus density times G times H1. H1 would be the height from the ground to the bottom of the bottom wing, right? Plus half density of air times V1 squared. P2 will be what? The pressure of the air pushing down from the top. P2, and then P1 is the bottom. Plus density G, or density of air G, H2. And H2 will be the height from the ground to the top of the wing, which is slightly more, but not that much more, you know. Plus half density V2 squared. So I'm going to venture to say H1 is approximately the same as H2. Not that much difference, because the wing is not that big. So H1 approximately equal to H2. So H2 is probably slightly larger, right? So a little bit less than or equal to H2. So what that means is we can cancel that part of the equation, the potential energy part of the equation. So now we can say P1 plus half rho V1 squared, and then density of air is the rho, is the density of the air. Because in this case, the fluid is not the water, it's just air that's flowing, right? Oh, I forgot P2. So P1 minus P2, which one is going to be the larger one? P1, right? P1 minus P2 is the difference of the pressure from the bottom minus the pressure from the top, right? So should that be a positive number?
Yes.
P1 minus P2, yeah, because it should be bigger pressure pushing down. So then that's going to equal half density of air V2 squared minus V1 squared. So now let's calculate what that is. Delta P, what's density of air? 1.30, right? And then let's say 270 squared minus 250 squared. .76 times 10 to the third pascals. Isn't that cool? Now we can go even further. We can say, let's say the airplane weighs something. What's the typical weight of the plane? 10,000 kilograms? Huh?
I don't know.
It can't be 1,000 kilograms, that's too light. 10,000 at least, you know. So I can say, calculate the surface area of both wings that the wings have to have so that the plane accelerates up at 1 meter per second squared. Given that the delta P is this. Calculate total surface area of both wings. If plane is to accelerate up at 1 meter per second squared. This is one of the most important applications of Bernoulli's equation, is air flight. That's how birds have applied Bernoulli's equations for millennia, right? And then we only figured it out 100 years ago. Just create a surface over which the air flows one way over the top, and air flows over the bottom differently. Create delta P. Let's see. So then how are we going to set that? Well, remember, pressure is force over area, right? So the delta F, the change of force over the wings plane, is going to be delta P times A, right? So delta P is equal to delta F over A, delta F equal delta P times A. So that's you get times A. So that's gonna, in a sense, that's kind of like your buoyant force on the plane, pushing it up, right? F buoyant, that is the delta F. So then what is going to be? Minus the regular weight of the plane, right? Because you have delta F, then you have the weight of the plane mg. So then that's going to be 10,000 times 9.8. We said the plane weighs 10,000 kilograms. That's going to equal to what? The mass of the plane times its acceleration. So the delta F, in a sense, I'm using the equation delta F minus mg is equal to ma. So let's see what we get for the surface area of the wings. That's going to give you the total surface area of both wings combined. Oh, okay, 10 to the third is gonna cancel what? 10,000 and 10,000. So it's gonna come out what? 10 times 1 plus 10 times 9.8 over 6.76. 100 over 6. Is that realistic? That seems too small. What is that? 11 times 10 is 110 over 7. What is that? 13?
15.
15?
Yeah, 15.97.
Yeah. Well, how long are the plane's wings? Typically, they're about maybe they're 20 meters by 5 meters, is it? Just try to visualize the wings. 20 meters. So that would make the 100 plus 100, 200. Yeah, way too small. I think that the mass of the plane we have 10,000 kilogram too light. Huh? Maybe 100,000 kilogram?
10,000 could be like a Cessna.
Yeah, that's very small. So we put 100. If we put 100,000, then the mass is 150. That's more like it for a commercial plane. Then you need more surface area. So the heavier the plane is, the area of the wings has to be larger. That's why the big birds, the birds of prey, they have larger wings. Right, the bald eagle. Right, and then small birds have small wings. Cool. Nice problem. I love that. Okay, let's do one more quickly. Now let's do that tube problem. Okay, so let's say there's pressure, a tube of water is coming like this at initial velocity 10 meters per second. Now in this case the fluid is actually water, and there's a huge amount of pressures pushing it at 2 atmospheres. Here it's open to the atmospheric pressure, 1 atmosphere. So you can kind of imagine as if this is a building, power manufacturing company or something. The machine is pushing it at 2 atmospheres, but this is open to the atmosphere. It could be a river or something, and it's dumping that to the river, you know. So the pressure here is open to atmospheric pressure, so it would make it 1 atmosphere. So now let's say the radius of this is 2 meters, and the radius here is 20 centimeters. So it's very constricted. So tell me what, if V1 is 10 meters, what's V2 gonna be? A simple, again, application of Bernoulli's equation, right? So pressure P1, P1 is 2 atmosphere. So this time 2 atmosphere, I have to change it to pascals, right? 1.015 times 10 to the 5th plus density of water. This one I should use 1,000, not 1, because once you bring Pascal, then you need to use metric units here. 1,000, 9.8, 50 meter plus half 1,000. And let's see here, this is going to be 10 squared, 1 atmosphere. Oh, this one H2 we can be 0, because usually you put your reference at the lowest location of the two. So H2 is just simply 0. Oh, you know what? No. I've given you too much information in this problem. I shouldn't give you what B1 is. Because if I give you too much information, then we might be not following the volume flow rate conservation. Because I've told you the radius of both of them already. Did I give you the radius of both? Yeah. So if I give you too much info, then I'm violating volume flow rate, right? So I shouldn't give you this guy either. But the volume flow rate conservation says what? A1 V1 is equal to A2 V2. So now pi times R1 squared, pi cancel. So now this is going to be, let's see, what was this? 2 meters radius. And then this one was 20 centimeters. So 0.2 meters. You see? So for this one, you usually should have 2 unknowns. And then there's 2 things that you have to follow. Bernoulli's equation and continuity conservation. You see? So then you have here 4V1, V2 is equal to 4 over 0.04. That's 100 V1, right? Yeah, 100 V1. Then you can put that here and solve for V1, right? So we could take that, bring it over here. So I brought this P, the pressure here, subtracted it from here. Then over here I could put half density of water. V2 is going to be 100 V1 quantity squared. Okay, now you can solve it, right? So divide everything by 1,000 if you want. And then this becomes 10 to the second, right? So then I have 101.5 plus 9.8 times 50 plus half V1 squared is equal to half 100 squared, 10,000 V1 squared. $10,000 minus 1 is going to be 9,999. And then you solve for V1 from there. Cool, right? So it's a good tube type problem that illustrates the pressure. So the problem can sometimes not give you P1, but then it would give you V1. Right? But as long as you have 2 unknowns, and then you're using both this continuity and you're using Bernoulli's equation, then you can solve any kind of those 2 problems. Okay. Okay, now we're finally done with chapter 13 and 14. So test is next Monday, and